triangles. I'll read that to you first. The law of cosine states that in any triangle ABC with sides A, B, and C, the following hold. Now, what this means is if you've got a triangle, so let's say you've got angle A here, B here, C here. Okay, what this is saying is that side A, of course, is going to be opposite from angle A, so that's going to be side A. Side B is opposite angle B, so that's over here. Side C is opposite angle C. So that has to be in place, and then we're ready to read the law of cosines. So law of cosines allows us to solve for any missing side, or it also allows us to solve for a missing angle if we're given all three sides. So the rule is that a square equal b square plus c square minus 2 times side b times side c times cosine of angle A. And this is just two different variations of the same rule, just depending on which side that you're solving for. So for example, if we look at the last line, the square of side C equals the square of side A plus the square of side B minus 2 times side length A times side length B times cosine of angle C. So the side length on the left side of the equation matches the angle inside the cosine function. And one way to help you remember these formulas is if you were to let's say suppose your angle C happened to be a 90-degree angle, so you would do cosine of 90. And if you recall, cosine of 90 is 0. So if that gives you a value of 0, then this term is gone. And you're left with c squared equals a squared plus b squared. Well, you should recognize that as a Pythagorean theorem. So basically the Pythagorean theorem is a special case of the law of cosines. Alright, so law of cosines is needed to solve a side angle side or a side 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 triangle. In other words, if you've got a triangle and you have two sides given and the angle between those two sides given, then law of cosines will help you solve the rest of the triangle. Or if you've got a triangle that just has three sides given and you know nothing about the angles, you can use law of cosines to solve those types of triangles as well. So let's look at an example. Example 1, I'm asked to solve the triangle, approximate values to the nearest tenth. And I've got triangle ABC. And then my side lengths, my side A is going to be 12. Side B is 10. Side C is also 10. So we've got three sides given, but we know nothing about the angles. And we have to solve for all of the angles. So law of cosines is going to get us started on this. I'm going to choose an angle that I want to solve for, and it doesn't matter which one you pick. I'm going to pick B, just because I'm in the habit of solving for B from the previous section. So let's say we want to solve for angle B. Then we're going to use the variation of the law of cosines formula that starts off with the square of side length B equals the square of side A plus the square of side B minus 2 times side length A times side length C times cosine of angle B. And we can substitute in as needed. So B we know is 10. We know side length A is 12. And we know side length C is 10. So substituting over here as well. So we have values in for every variable, and we just have to solve for angle B. So that gives us 100 equal 144 plus 100, so that's 244, minus 2 times 12 is 24, 24 times 10 is 240, times cosine B. And let's subtract 244 on both sides. So that's going to give us negative 144 equal negative 240 cosine B. And then divide both sides by negative 240. That gives us cosine B. And if we were to simplify negative 144 divided by negative 240, that would give us 0.6. So we have, and I apologize, I'm running out of space here. We have, I'm going to have to bring it back up here. 0.6 equal cosine B. Then we need to do cosine inverse, so, or arc cosine of 0.6 equals B. And we can calculate that. Of course, make sure your calculator is in degree mode. And you're going to do cosine inverse of 0.6. And that should be giving you 53.1. We were asked to round to the nearest tenth. So angle B is 53.1. Alright, so how can we get the next angle? Well, you could do the same process again to get the second angle, or if you prefer, you can go back to the law of sines. Now that you've got, we know that angle B is 53.1. If you got used to using law of sines in section 8.1, then you're ready to do that here too. So for law of sines, I need some more paper, so let me get that real quick. Okay, so for law of sines, where are we? Law of sines, we know that, so let's say we're going to solve now for angle A. So to solve for angle A, using law of sines, I can do side length A, 12, over sine A, equals, and then I need an angle, so I'll go with the one that I just found. So we'll do side length B, which is 10, over sine of 53.1. We can cross multiply, and I'm having a hard time keeping all this on the screen for you, but so we'll have 12 times sine 53.1 equals 10 times sine A. Divide both sides by 10. And now take the inverse. So I'm typing in 12 times sine 53.1, close parentheses and enter. Now divide by 10, enter. So I'm getting that 0.95962, blah, blah, blah. Now we do sine inverse of that. So second sine inverse, second answer. We're getting 73.7 when we round it to the nearest tenth. So angle A is 73.7 degrees. Okay, and then, so now we've got two of our three angles. 73.7 for angle A, so that's my original triangle there that I've just done. So the only thing left now to solve for is angle C, and that's easy because we've got these two. So all you need to do now is subtract the two known angles from 180 degrees. So 180 minus 73.7 minus 53.1. And that gives us a result of 53.2. So angle C is 53.2. So that's part of our answer, that's part of our answer. And then the result that we got for A on my other page, 73.7. It's okay that if you were to add up our three angles that we got, they may not exactly add up to 180, but that's okay because we rounded. So when I add them up, mine actually are adding up to 180, but if they don't, it's okay if you had to round in a problem. So, but that is how we got that answer. So there's all the work for that. So step one, we did the law of cosines to get the missing angle. Once we had that, we just went back to the techniques that we did in section 8.1 using law of sines, and then we subtracted the angles from 180 to get the last remaining angle of 53.2. Alright, and that's it for example 1. Okay, the second topic in this section that we'll discuss is, I'm not sure how this is pronounced. I'm going to pronounce it Heron's area formula. This is a formula that we can use to find the area of triangles when we have 3 sides given and we have no information about the angles. So it states that if a triangle has sides of lengths A, B, and C with semi-perimeter S equal 1/2 of A plus B plus C, then the area A of the triangle is given by the formula A equal the square root of S times S minus A times S minus B times S minus C. Now, what does that mean? First of all, what is semi-perimeter or semi-perimeter? Well, you know that perimeter means you add up all the sides, all right? Semi means that they multiplied it by 1/2, so it's just half of the perimeter, just like semicircle is half a circle. So we'll have to calculate S by adding up all of our side lengths, which we will be given, and then dividing that in 2, or dividing it in half, or dividing it by taking half of that. Alright, and then I'm using a capital cursive A for my area so that I don't confuse it with the A that I'm using for my angles. And we'll just do these calculations. You'll probably get large numbers when you're working through these problems, but the computations are not difficult. So here in our second example, we're going to find the area of the triangle with 3 sides. A equals 76.3 feet, B equal 109 feet, C equal 98.8 feet. And we're going to use this formula. So we first have to find the semi-perimeter. So add up your side lengths and divide by 2. So we got 76.3, 109, and 98.8. Okay, that gives me 284. If I divide that by 2, I get 142.05. So I have S equals 142.05. And I just basically plug it all into the formula. So we've got A equal square root of 142.05, parentheses. Alright, we're going to do S minus A, so 142.05 minus 76.3. I'm going to write it all in for now so you can see where everything is coming from. Okay, then I need to do S minus B, so 142.05 minus 109 times S minus C, 142.05 minus 98.8. And that's just crunch the numbers from here. Okay, so we've got 142.05. Okay, S minus A is going to give us 65.75. S minus B gives us so that's 142.05 minus 109 gives us 33.05. And 142.05 minus 98.8. That gives us 43.25. Okay, now we need to multiply all that together, and then we'll take the square root. So 142.05 times 65.75 times 33.05 times 43.25. That's giving us a very big number, but that's okay. So I'm going to write down the digits and then I'll read what it is. So So it's 13,350,409. Then take the square root of that. Okay, square root of that is going to give us 3,653.82. All right. Since they had, let's see, they had their digits to the nearest tenth in the original problem, so that's probably what we're going to do. They didn't say how to round it, so we can say 3,600, and it looks like they did significant digits for this and rounded it to a whole number, or rounded it to a 10. So, all right, so we're getting 3,653.82, and of course that would be in square feet. So that answer is good. You might run into a little bit of a snag when you go to type this into my math lab for this particular problem, but we will talk about that if that happens. Okay, so that's the way the Huron's area formula works when you're given a triangle that has all three side lengths but no angles. Alright, and then I'm going to do just a couple of more examples with you in a moment. The last type of example I'd like to do with you is from the concept preview from the exercises in section 8.2. We're told to assume a triangle ABC has standard labeling. Okay, that just means that you've got angle A, angle B, angle C, and then your side lengths are lowercase a, lowercase b, lowercase c, and the side A, for example, is opposite angle A. So first we have to determine whether we have a side angle angle, angle side angle, side side angle, side angle side, or side 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 given. Okay, that's not hard to figure out. And then part B, decide whether the law of sines or the law of cosines should be used to begin solving the triangle. So we're going to do a couple of these. Let's do 1, 3, and 5, and maybe 7. Alright, so for number 1, lowercase letters, of course, are side lengths, and uppercase are angles. So you see that you're given 2 side lengths and 1 angle, and the one angle is, let's draw a picture of this. So in number 1, if we draw a triangle, let's look at where everything is positioned. If you've got, so typically you would have angle A, angle B, angle C, like this. Side length A, side length B, side length C. Okay, in number 1, we're given this measurement, and we're given angle C. Okay, well notice the angle C sits between side lengths A and B. So that means that you've got angle between your side lengths, so you can say that's a side angle side scenario. So we've got the side angle side scenario here. Alright, then the question is this a situation where we should use law of sines or law of cosines? Well, if you've got an angle that sits between 2 side lengths, you're going to go with law of cosines, which was what we discussed in section 8.2. If you think back to the problems in section 8.1, we did not have any that we were given this precise type of arrangement. So this will be a law of cosines problem. In number 3, we're given side length A, side length B, and angle A. So let's draw this one. So I'm just getting this set up real quick. So we'll draw this one the same as we did before. Angle A, angle B, angle C, side length A, side length B, side length C. And in number 3, we are given A, side length A here, side length B, and angle A. Okay, so for number 3, this is what our picture looks like. We were given these 3 pieces of information. So what type of triangle do we have? We've got 2 side lengths and we've got an angle. The angle does not sit between the 2 side lengths. So this is a side-side angle problem. Side-side angle. Okay, and this is that ambiguous case that we worked with in section 8.1. So this will be a law of sines problem. Okay, so you should hopefully you recognize that as that ambiguous case where you had the angle and you had two side lengths, and then you had to decide if you actually had a triangle or not, depending on how long this side length came out to be. Okay, and then for number 5 we have, let me see if I can draw this in here. All right, so for number 5, A, B, C, lowercase a, lowercase b, lowercase c. All right, we are given angle A, angle B, and side length C. So all this over here. So this time we've got a side length that sits between two angles. This is an angle side angle arrangement. All right, and which scenario does this give us? If you've got angle side angle, this is going to be a law of sine situation here. So this is one like you would have done in section 8.1, and this one was a very straightforward calculation. You didn't have to do a whole lot of extra work for this type of problem. It was one triangle and you just found the angles and the side lengths. Okay, and then let's look at number 7. Number 7, you're given 3 side lengths. So, of course, that's going to be the side situation, SSS. And which law would we use for this one? Well, this is like we did in example 1. We saw an example where we had 3 side lengths and we didn't know anything about the angles. So this was the law of cosines. So it was the side, and it was the law of cosines. So I hope that helps you kind of get a decent understanding of what's going on in section 8.2. I don't think the exercises are terribly difficult for this section. So I will get those posted for you to be working on over the weekend, and that is section 8.2. All right, thank you.